Okay.
Oh, hello, Professor.
How are you?
Hi, I'm fine. So today you sent email and you said that today you will not able to take a class.
I will not be able to teach a class. I will wait
Okay.
until everyone connects and start.
Oh, okay,
And
okay.
then I have a schedule conflict. I need to be at the other meeting that I cannot shift. But it's only one time event.
So Professor, in next next week or we need to submit a one homework. So uh, we just need to write on a paper, then scan and then send it to you.
Scan and send to me. And it is very, very simple.
Okay.
It's like a couple of pages, and you can discuss it with each other. So it, I do not have a goal to like lower your grades. It's more than for me to check that you all understand what we
Okay.
discussed.
Yeah. So today I come back from my office early and this is my apartment.
Oh, I see. And I will be soon with public.
Yeah.
Слышь, ты, сделал. I'm talking to the Professor Kilina. She will be substituting me. Да, да. So I will try to memorize it with time, but let me guess. You're from the group of Professor Venji here?
Yes.
Okay. But you started just this semester and you do not have a project yet.
Um, Professor, last time, 2 or 3 days ago, he said that I will start to work on Vitrimar.
On what?
Vitrimar.
And who is it? Please teach me.
Um, he sent me few papers. Then I just started to read those papers. Then let's see.
But what is this compound?
Mm,
I just never heard this word. Is it solid, liquid? Is it gas?
Professor, it's one kind of a polymer.
Okay. Does it conduct electricity or it is dielectric?
Uh, Still I'm reading paper, so
Okay. Okay.
maybe with at the end of this week I'm able to grab something from those papers.
I see. I see. Do you know what is the color of this polymer?
No, 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 no.
Okay.
Still,
Yeah, it is. It is good that you have a project. I'm happy for you. Do you live far from campus? Is it on walking distance or you need to ride a bus?
bus. So now I'm staying in University Village.
Okay, so it's not very far, but it is much more
Not
comfortable.
very far, but because of this weather, and I'm new student, I don't know the walking distance very well. So that's why I'm using bus.
I see. Hello, Sarah. Nice seeing you connected.
Hello, Dr. Clean. How are you?
Very good, very good. Thank you. I will not be able to teach the lecture, but my close collaborator, Professor Svetlana Kilina, will help and deliver a little bit of lecture. So she'll connect and start sharing slides soon, and I'll just wait until everything starts and then go to my meeting. It will be only one time. All other meetings should be okay. But I'll go into public place.
Okay.
So I need to repeat it for myself several times to learn. So which, Sarah, do you have a project that you are working on in your research group?
Yes, currently I'm working on clay modeling.
Oh, okay. You are doing clays. Okay.
Yes.
And you are planning to deposit biopolymers.
Yeah. Yes.
Yeah, very interesting. Very interesting. So you are doing force-field molecular mechanics right now?
Yes. Right.
And, how big is the unit cell? How many atoms?
Currently, I'm working on the coarse grain modeling. It's around 200,000.
Okay, so it is not atomistic. It's more like finite differences.
Yes, it's coarse grain modeling.
Mhm.
Yeah. And beside that, I'm looking for all atomistic model of clay, but I haven't started yet. But in future, I'm going to work on it.
Very good. It's a very appropriate project to contribute from this class.
I hope so. Yeah, I was talking with Dr. Shah, and he suggested to work on modeling of, for example, clay with adsorption of some gases like arsenic gases and
Mhm.
absorption. Yeah, and by DFT calculation, maybe in this course or some others model. I don't know which model, but here that was Dr. Shah's suggestion.
Mhm. Yeah, it's very reasonable. So in addition to I think it is Leah, right?
Want to change the name. My husband used my
Yes, I am a little
Lee.
surprised.
Okay. Okay, I just changed it.
Okay.
And this is it's me now.
Yeah, good evening. So I'm happy to find that we found good times during the week when most of us or everyone can join.
Yeah, it's perfect.
I have a question. Is it possible to change the Friday time to other days, like Monday or I don't know? Because in Friday I have a lot of meeting. It's
Um,
midday for me.
I am open. My schedule this semester is not as tight, but we need to do it more democratically and talk to everyone in class. If you find another match when everyone agrees, I will be willing to.
Yeah,
In
I
this,
saw in the picture that you sent us that most of the students was agree with Monday.
we can do it. Maybe at least for the half of semester, because second half I teach another course and it will be Monday morning. But we'll find way, and let's keep discussing. So I will easily change to Monday if everyone is for it.
Yeah, okay, thank you.
Let's see. We do not have Stephen and Boston on the link, but maybe maybe they will join later or they plan to watch it in recordings. I'll be out and in one more time before I finally depart.
Hey, hello guys. Here is Dmitry.
Yeah.
He was just in another room.
Let me introduce Professor Kilina. So,
Hello, Professor.
Hello.
So she will deliver today's lecture, and she will use a little bit different view on the same things we are doing. So models of molecules and looking on electrons and nuclei and how to connect them with quantum mechanics. So wishing all of you pleasant evening with inspirations of science, and looking forward to see you on Wednesday.
Okay, yeah, and this is of course a substitution. I hope it will be really maybe once, maybe a few more times, but not really. I'm not really your. I'll say I'm not co-teaching this course. So I will be sharing the slides. You already have slides from Professor Kilin. My slides are different, and honestly, I think they are more beautiful than his are. So he will be. I will deliver these slides to him, and he probably will also post the slides on the website, or just send the slides by email to you. So you will have closer connection to the. By conceptually, they're exactly the same as what you got already from Dmitry. They just have a little bit format issues. Oh, actually, they have different formats. It's not really issues. So that's why I think later on, if you get these slides, probably it would be easy on your side. So let me share my slides. So you can see them, right? No, you don't. I don't think you can. Yeah, now you can see them.
Yeah.
Perfect. Okay, so I'm just welcoming all of you who are joining us. I think there should be 6 students at least, 3 more, but we have 3 of you joining this lecture for today. It's lecture number 2.
Yeah,
And
it's lady class today.
okay, so but yeah, and we will be talking about Schrödinger equation, and we start with Schrödinger equation, how we write the Schrödinger equation for atoms, and then go to the Schrödinger equation for molecules. So main questions which we will address today would be for this topic, for the Schrödinger equation. We start with just general idea, what we call the equation of motion for a particle. And by a particle, you can think that you treat a particle in a classical view. We can call it as a classical particle, or it can be a quantum particle. So in a case, if you think about classical particles, then it would be the equation of motion is nothing else as just Newton's equation. And most of you, of course, are familiar with this. If you think about that the particle is a quantum particle, then this is where we need the Schrödinger equation, which has the meaning is just the equation of motion for the quantum particle. There are 2 types of Schrödinger equation. And in this class, you will be dealing, I think, with both. But for your practical point of view, the things which you will be really doing with computations, they will be focused on the stationary, non-time dependent, time-independent Schrödinger equation. If you will do some project which includes the processes which are changing with time, I don't know, absorbing of light, charge transfer, or many other chemical reactions, something which really requires the change in time. Then, of course, you need to use time-dependent Schrödinger equation. So most of discussions, not only today, but probably for the most of the discussions in this semester for this class will be, of course, about time-independent Schrödinger equation and their application. But I think it would be good idea that you know that there's also time-dependent Schrödinger equation, and probably late by the semester, Dmitry, Professor Killing will introduce this time-dependent Schrödinger equation. So when we say Schrödinger equation, it is also a valid question to ask which form do you want. Like if someone asks you to write the Schrödinger equation, you will be really very smart if you ask the question, which form do you want me to write it? Operator form or differential form? Then people will be completely impressed by your knowledge, even if you don't write the Schrödinger equation. Just this question will be good enough to make an impression. So yes, we can write Schrödinger equation through operators, or you can just write it as mathematicians do using, mainly it will be just differential equation. So when we say operator's form, of course, it's also mathematical term. If you didn't use it before, if you didn't have classes which really emphasize this operators in mathematics, I will give you a brief introduction. It's really simple idea. Any operation on functions, you can call this as an operator. They have special properties, which again, I will address in this lecture. Just as a review, I expect that most of you should know this, or at least when I start talking about it, you will get like, oh, this is what we call this. So this information should be really familiar to you, but I just review it just in case, so we will be all on the same page using the same language. So Schrödinger equation in its operator form looks very, very simple. It's really just 3 letters. H, 2 terms, 4 letters. 3 letters because 1 letter is just used twice. So it is H psi equals E psi. But of course, the meaning of this is not as easy, and to understand its meaning, it's better to present it in the form of differential equation. And really, so this is what really we do when you write the codes, if you really need to do these solutions, not in paper, but really run the program, which will do some calculations for you. Then, of course, we use this differential form rather than operator form. So we will talk about it today as well. And we finally getting, after we're familiar with the techniques, with the tools you need to know for writing the Schrödinger equation, we also will go to this terminology of Hamiltonian. This is what I said, the first term, H psi, H stays for the Hamiltonian. Again, the concept of Hamiltonian is very simple. It's just an operator of total energy. And I hope all of you know what is the total energy. If not, this is a discussion today, will help you to figure it out. Knowing how to create this operator of total energy, you really can write this Schrödinger equation without any problems. However, to solve the Schrödinger equation is not as simple. And there are, so far, analytically, we can solve only Schrödinger equation for a single electron system. If there are more than a single electron, there's no way to do it just by hand. We need to do it numerically. Plus, we need to imply simplifications, some approximations to be able to address such a complicated, mathematically complicated equation. Okay, so let's start from the beginning. Equation of motion for classical and quantum particles, how they are different and what this means. I think I will be not the first person telling you that when we say electron, is it a particle or a wave? How we treat electron, as a particle or is a wave? What do you think? Okay, if you think that this is a particle, say yes. Yes? If you think that this is a wave, say yes.
Yeah. It's a particle, and at the same time, it can be described as a wave.
Yeah,
Them.
exactly.
We can describe them as.
Yeah. So if you say that it's a particle, and if you said yes, you're right. But this is only half of the story, because it's also a wave. You can really think about it simultaneously as a particle and a wave, and it shows both properties simultaneously because it's a quantum object, right? So we can say that electron equals, means it has properties of particle and the wave simultaneously. If we think about particle, it's really what we think in classical point of view. I think if you understand what is a particle, it's an object which has some mass and which moves with some velocity. And from this point of view, the goal for any equation of motion, it is to know where the electron is at some moment of time. So we need to have the equation which we solve, and then solving this equation will give us the information of the coordinates where the electron is located at this specific moment of time. This is a way this formulation works. Intuitively, it's clear, right? Equation of motion, you can really apply it. Let's say you are driving on a car. If you know the speed of your car, and if you drive with same velocity, you, of course, with a simple equation, you can figure out how far away you will go in 10 minutes, in 20 minutes, in 1 hour, if you're driving at these conditions, right? Just from a simple equations, mathematical equations, this can be done. So this is our classical approach to answer this question. However, if we think about the wave, here we get in a problem with this formulation, because when we say where it is, the wave is something which is already spread over. It's not really located at some specific spot, right? So it's kind of really strange if I ask you where the wave is of, if you think about waves of water, right? The surface of ocean, for example. Where is a wave? Oh, wow, it's really everywhere, right? It's spread over. You really don't have a specific space where the wave is. So, and this is completely true, even if you think about it as not wave on the ocean or sound, wave from the air, compression or depression of the density of some gas, for example, right, which creates a sound waves. If you think about electron as a wave, or if you just think about electromagnetic wave, something which really can touch, in any case, this idea about where it is, instead of just saying where it is, what are the coordinates, we need to think about probability. What is the probability to find these coordinates of this wave at some moment of time? Probability gives us kind of a distribution, right? What we also call probability density distribution function, which is having maximum somewhere and minimum. So it's spread, and the maximum corresponds to the position of the most probable position to find the electron, maybe 90%, maybe 80%, you can find it there. And then these tails of this distribution, where they go to the minimum, it means you have less probability to find it, unlikely to find it. And where you really have zeros, it means no way to find it somewhere there, right? So you can figure out probability means that it's not necessarily will be there, but you can be more certain or less certain, depends on this percentage or probability distribution. So in both cases, we can think that our main goal to find the position at some moment of time. But if we talk about quantum objects, a wave, thinking about electron behaving as a wave, you need to correct not just position, but probability to find this position at some moment of time. So to answer this question, we need to set up the equation, to write the equation, which we also can call the equation of motion. For the classical case, it would be just equation which is based on a sad law of Newton's law. Anyone remembers Newton's law, the very famous Newton's law, dealing with force and acceleration. F equals
ma, mass times the acceleration.
Where m is mass and a is acceleration of the particle, of the classical particle, moving with some velocity and acceleration. So we will have wave equation in the quantum case and Newton's equation in the classical case. So for Newton's equation, as we already said, you can just write F equals ma. This is right equation, 100% correct. If you answer this question like this, I think your teacher, Dmitry, will be really happy with it. However, it's completely impractical. You cannot solve problems just using F equals ma, and of course this will be not practical to apply this equation for writing the codes, doing these calculations for you. Why? Because this A is not defined. You can think about mass as being a constant for specific object. Mass is not really changing, but it's unclear what is force and it's unclear what is acceleration in this formula, right? So that's why we need to present it in a more practical way. For practical way, we will define force as a derivative from the energy, potential energy. And this is the actual definition of the force. Force is a derivative with respect according to the coordinate. We know it's x, y, z, but in 3 dimensions we can characterize just the distance between the initial position of the object and its coordinate at some other position, right? It would be kind of this r as a distance, which depends on the coordinate x and y and z. So we can take a derivative from the potential energy. Potential energy is the energy of interactions. And this derivative will be the force, actually with a negative sign in front. So now to represent the force, we just need to know the potential. And then, of course, taking the derivative from the potential, if it's known, if the form of potential is known as a function of r, right? V of r means some function. If we know this function, to take a derivative is not a problem. So we know how to deal with this. And of course, you also can program it. So your machine, your computers can do this procedure as well. Then m is taken as constant, since it's not really changing for the object in regular situation. And then acceleration, by definition, is a change in the velocity. And velocity is a change in the coordinate. That it means that the acceleration would be change of the velocity, or you can say it's a change of the coordinate. So it's a second derivative, twice of change, means a second derivative with respect to time of the coordinate, right? So your coordinate is changing with time, it's velocity. So first derivative would be velocity. Then if you want to answer the question, what is a change in the velocity with time, if the velocity is not constant, then it would be acceleration. And it means you're taking a second derivative of the coordinate of this distance r with respect to time. So, and now this is what we call differential equation. You have a function v which depends on r, and this function depends on r with some time. Actually, it depends both on time and coordinates. And then you just need to solve it as a differential equation. So if you took mathematical classes with the name differential equations, then you probably even know how to solve it. If not, believe me, there are methods specifically designed to solve most types of differential equations. How to solve them is pretty well-known procedure. And this is, again, you can put it as a coding in the computer, and then computer can really do this procedure for you if you know the potential. You need to know the potential means you know to know the function of potential energy, how it is changes with coordinate and with time. So in other words, these things really nothing exciting. Maybe you don't know how to do it, but advanced people who are really working with mathematics, they really, for them, this is not a problem. So there are existing methods which can do this easily. What about wave equation? This is where we go to the quantum mechanics Schrödinger equation, telling you the equation of motion, which actually has the same meaning as just the wave equation, because in this case, we want to know everything about the wave. The probability to find the electron as a wave after some time, or at some specific time. So for the wave equation, it's a little bit more complicated to write and to, of course, to solve, comparing to the classical Newton's law. And this is, I will show you in my next slide. But in both cases, either Newton's law or the Schrödinger equation, which is the same as the wave equation, neither of them can be derived. Right? F equals ma, it's something which was found through the observations, empirically kind of, right? Same for the Schrödinger equation. It just was the wave equation. It just was said, oh, empirically it looks like it follows this equation. So this is nothing which can be derived. It's just coming as a postulate, same as Newton's law, said Newton's law, in the same way as Schrödinger was postulating his equation as you can also call as a wave equation. So, as I already said, there are two Schrödinger equation. It's just the equation of motion for the quantum particle. Or you can say it's a equation of motion for a wave, because quantum particle behaves simultaneously as a wave and as a particle. But there are two of them. One is time independent. It's also called stationary equation. And one is time dependent, general form. As I already said, we mainly, or at least most of this semester, you will be focused on the time independent Schrödinger equation. And this is what I will be talking for my next slides. You might really go to the time dependent case much later, sometime close to the end of the semester. It's a simple four, or actually three different letters, two terms, h psi equals e psi. Psi stays for the wave function. As we already said, it's equation for the wave. And the wave is characterized by the function, by what we call wave function. So psi is a wave function, which depends on a coordinate. Here I'm showing it depends only on x, which means we talk about one-dimensional case, when everything is just like a stream, for example, right? But of course, you can also have two-dimensional case, three-dimensional case. Then it would be dependence on the x coordinate, y coordinate, z coordinate. Also pay attention this kind of notations, the head, or wherever this head on the top of the H letter. This notation is notation for the operator. It's just showing that we have an operator acting on the wave function, and we're getting the same wave function, which is just multiplied by the E. E doesn't have this head. It means it's not an operator. If it's not an operator, then it is just a constant. So you have a constant E times the same wave function as was your operator, H, acting on this wave function. So looks pretty simple. You have some operator, which we call Hamiltonian, by the way, which acts on the wave function which characterizes the wave. And after this action, you're getting the same function multiplied by the constant. In this form, what we call the wave function or the wave equation or the Schrödinger equation. In its time-dependent form, it's just having this dependency on time as a derivative of time, again, of the wave function. And here is some Planck's constant, and I, it's imaginary, how we actually call it, imaginary number, I, yeah, imaginary number for imaginary values, this I having the same meaning. I psi, like a constant, derivative with respect to the wave function equals, again, operator, it should be head, just missed here, operator acting on the same wave function. And again, don't worry so far about this. It's more complicated because now you have to take a derivative with respect to time. Here there is no time dependency, only coordinate dependency. And of course, your h psi looks very similar to what you have on that side, right? But you also need to take the derivative with respect to time. So it's more complicated case. We will consider it later on. Right now, let's talk about the simpler stationary Schrödinger equation. So it has this operator Hamiltonian, which has a name Hamiltonian, and it has a physical meaning, just operator of the total energy. And by the way, this constant E has just a meaning, the value of the energy. So psi is a wave function, H is the operator of the total energy, which has a name of Hamiltonian, and E is a constant which characterizes the value of the energy of some specific electronic state, right? And now I really can say that psi is a wave function in general. You can call it wave function in general, but in our case, it's really the wave function which characterizes the electron. Since for this class, the main object which you're really interested in would be electrons in atoms or molecules. And we need to know how these electrons are moving in atoms and molecules. So, we're interested in the stationary Schrödinger equation. to figure out the probability to find an electron at some moment of time. And yeah, we're interested, probably we start with atoms, because we know molecules are constructed from atoms. So knowing about atoms is already helping you to move to molecules. So we will need to solve the stationary Schrödinger equation, which is just a wave equation for a wave. And by the way, it's not just any wave, it's for the standing wave. Do you have any ideas how the standing wave is different from a traveling wave?
Yeah, the transverse wave has a peak and top, but the standing wave is longitudinal, called longitudinal wave.
Okay, think about, you can imagine the waves on the surface of water, right? About ocean. And they are, like, if you really look on one specific peak, like they look like sine function, right? With maximums, minimums, and nodes, where you have zero kind of. So they do this kind of oscillations. And if you really take a look on a single bump, right? It of course will be moving with time. You can imagine. So let's say you focus on a specific bump, but with time you will see that it's not standing on the same place, it is moving. If you can mark it with some color, you definitely will see that it moves. This is a traveling wave. Why is it moving? In case of what it will be transferring the mass of water, will kind of particles of water will be moving with time through this wave behavior. You also can imagine sample even as alternative for the standing wave. You can imagine the case, let's say you think about guitar. You know what is guitar, right? The string, let's just look on a single string on a guitar. It's fixed, its ends are fixed. Now if you really try to make a sound, for sure what happens with it starts oscillates, also making this kind of oscillations if you look on its motion, but its maximum and minimum stays kind of on the same position. In this case, there's no really any redistribution of the mass or the energy in a space. It's just shifting its position of maximum and minimum, staying kind of on the same wave. And that's why it calls a standing wave. Its maximum minimum is just changing its position. What was maximum now is minimum, what is minimum now is maximum, right? But there is no really motion or traveling in terms of energy or mass when you have the standing wave. So Schrödinger equation is not just equation for any wave, it's an equation for the standing wave. I forgot to mention it in the very beginning of the slide. And then for electrons in atoms, they behave again not just as a wave, they behave in atom because they feel the interaction with nucleus, with a positive charge on the protons. So they kind of spin out, doing some complicated motion due to this attraction around the nucleus. And this interaction results that electron behaves as a standing wave, not as a traveling wave, but as a standing wave. So technically, the Schrödinger equation would be the equation which characterizes standing wave, the motion of the standing wave, which is the same to say that would be the motion of the electron in an atom, because electrons in an atom behaves as a standing wave. So, and this explains, actually, as we already said, standing wave doesn't have any dissipation of energy, changes traveling of the energy of the mass. And of course, when electron, we're thinking about the energy, change in energy of the electron. So there's no dissipation of this energy with time for the standing wave. And this explains why, when we know electron is kind of moving inside of the atom, but it doesn't release energy in form of the electromagnetic wave, which technically, if it was not a standing wave, it should really, any moving charged particle should release the energy in form of the electromagnetic wave. And then it's losing its energy. And then it becomes not stable. But we know that electrons in atoms are stable. They can survive hundreds of, if you're not talking about radiative isotopes, then, which is a story about nucleus, not about electrons. But electrons in atoms are very stable. They exist in this form forever, right? They're not dissipating energy. They're not losing their energy and not getting closer to the nucleus with time. Why? Because it's a standing wave, which is not releasing any energy. Doesn't propagate or release energy. Atoms are stable. Electron behave as a standing wave and can be described with a Schrödinger equation. Okay, so as I said, Hamiltonian is an operator of total energy. Then you need to just remember what is the total energy. Total energy is a sum of kinetic energy and potential energy. Do we know what is kinetic energy? What's the physical meaning of kinetic energy? If I have, like for example, I'm sitting right now, do I have kinetic energy? No, because kinetic energy is the energy of motion. Because if there is no change in the, if there's no speed, if there's no velocity of a particle, if it's in a rest, then kinetic energy equals to 0. So kinetic energy is the energy of motion, and potential energy, it's the energy of interaction. What would be potential energy of the ideal gas? If we consider ideal gas, what would be, can you say me immediately, what would be the value of potential energy? Is there a potential energy for the ideal gas? Okay, do we know what is ideal gas? Why we call the gas ideal?
So what I know, it's the molecules will be stable, not interacting by in the normal conditions like temperature and.
Yeah, we think that ideal gas is a gas where atoms or molecules, the particles of this gas, are so far away from each other that they really don't interact with each other. And you can really think if you take a very diluted gases with a very low density at normal conditions, if you know really have, they're not pressed, they really can be far away from each other. Most of the gases behave as ideal gases because the distance between atoms or molecules are really far away and they not really interact. And of course, we're not talking, you can really think about inert gases would be a good example, such as hydrogen gas, helium, argon, krypton, radon gas, inert gases. They have only, they come in from atoms, they don't really create molecules. That's why they're called inert gases. They don't like to interact, and they really the atoms are so far away from each other that they don't really see each other, they don't have interaction. Potential energy is the energy of interaction. If there is no interaction, potential energy equals to 0. For any ideal gas, potential energy is equals to 0, and you have only kinetic energy since atoms are moving for the ideal gas with some velocity. However, unfortunately, most of our systems, most of our things, materials which we are working on are not ideal gas. We have liquids, we have solids where atoms are really close to each other. They do interact with each other. So potential energy is an important term. You cannot just neglect it. And it's really a complicated term to really do. Most of the complications coming because of this potential energy interaction between different atoms and between different electrons. Even if you look on the single atom, just interaction between different electrons also results on the potential energy.
Can I ask a question, please?
Yeah, please.
So can we say the water molecules interact between each other in the liquid, so the the water will have potential energy then?
For sure, yes. Any liquids actually will have already potential energy, because if you have a liquid, atoms and molecules are already close to each other. They're not ordered, they're disordered, but they're close to each other, so they already feel each other and make this interaction. And in case of water, it's especially true for water because of two reasons. We know what water has: 2 oxygens, one oxygen to hydrogen, right? Yeah. And it has a very strong dipole moment. It's a very polar molecule because oxygen is negatively, very electronegative, so it's more negatively charged, and hydrogens are more positively charged. So you have redistribution, and it looks like water molecule. This is my hydrogens, this is my oxygen, like this. Mm-hmm. So water molecule like a triangle, right? Hydrogens having kind of plus, oxygen having minus. So you have a dipole moment distribution of this more negative guy on the top and more positive guys on the bottom.
Yeah.
Results on the strong dipole moment, which means that we have very polar molecule, and then they interact through the dipole-dipole interaction.
Okay, so can we say the dipole moment interaction between water molecules results and the potential energy inside?
They definitely will have potential energy, and this potential energy will be in the major contribution to this potential energy for water would be due to the dipole-dipole interaction. The potential energy in this case is dictated by the dipole-dipole interaction between water molecules. Plus, they also do this hydrogen bonds. If you were taking chemistry, you probably know what is a hydrogen bond. It's a not really actual chemical bond. It's a bond between different molecules. Hydrogen from one molecule interact with the oxygen from another molecule, which means they feel each other through this, again, dipole interactions. And they feel each other so strongly that they really move together, right? You can't really treat different molecules independently. So actually, this is another reason, even if you put it in a not liquid, if you not look on water as a liquid, if you look at it as a gas, vapor, steam, right? Vapor of the gas of water means steam. If you look on a steam, it also doesn't, even at normal conditions or even at low concentrations, it will not behave as ideal gas because of very polar character of water.
Excuse me, doctor, what's this gas?
You just put water in a gas form, and
Okay.
steam. If you boil water, you see this kind of white cloud.
Yeah.
We call it steam, which means it's just a gas form of water. Chemically, it's the same molecule, H2O, right? And again, because of this very strong polar character dipole moment, even in the gas form, the interaction would be strong enough, and it will be not a good model for ideal gas. It means steam usually has to be treated with potential energy, which means it's not ideal gas. But okay, this is not a story about gases. So we have both kinetic energy and potential energy as a sum for the total energy. Now, the only thing which we need to say, because we talk about operators, then we need to say that it's operator of kinetic energy plus operator of potential energy. What is operator of kinetic energy? We said it's a motion, and in quantum mechanics, the kinetic energy is presented as you can also say it's an operator of momentum, and I think Dmitry already talked about it, probably in the first class, and later on it's also we'll be talking in the second class, in next classes. So kinetic energy can be presented through momentum. It would be actually just momentum over 2m. M is mass, momentum divided by 2m. And momentum can be presented as a derivative over, actually, momentum squared for the kinetic energy. Momentum can be presented as a derivative with respect to the coordinate. So the kinetic energy will have this form. Operator means it's some mathematical action on the function, right? In this case, kinetic energy is a derivative with respect to the coordinate and a second derivative with respect to the coordinate for whatever function you want to put here. Since we talk about electrons, this would be the wave function of the electron. Let's say if it moves along one-dimensional case for simplicity, then it would be just the coordinate x, and of course it probably changes with time. So this would be the kinetic energy term. And this is potential. Potential really might have different forms. It can have a form of parabola. If you talk about kind of more for the vibrations, it can have step form, or it can have a form of like a hydrogen atom, I would say like V-shaped type of form, and so on. So it really depends what kind of system you're talking about, where is it a single electron atom, many electron atom, and so on. So we cannot really put this function of potential so easily. You need to know more details about the potentials. That's why we just put it as V, as some function, which also is kind of acts on the psi. So kinetic energy is second derivative with respect to the coordinate on the function, on the wave function. And for the potential energy, you really need to know the form of this potential. And then multiply by psi, by the wave function. This now Hamiltonian acting on the psi, because this term plus that term gives you total operator of the total energy. And then this is the rest of the Schrödinger equation, constant times psi. So this is again wave function, characterizing the probability of electron being at coordinate x at the moment of t, at some moment of time. So this is a wave function of the electron. This term is kinetic energy. Pay attention, it also includes minus. This is Planck's constant divided by 2 pi. This kind of slash on the h means it's Planck's constant divided by 2 pi. Mass, 2 is 2, and the second derivative with respect to the coordinate. This is operator of the kinetic energy, and this is operator of potential energy, which you need to specify what exactly the form of this potential is. Can be parabola, can be some complicated function, but it has to be specified. So this is operator of the potential energy. And this is a constant characterizing the energy of the electron at this specific state, at this specific coordinate, having this specific potential and kinetic energy. Now, this is expression for the Hamiltonian kinetic term of the energy plus potential term of the energy. And this is again the Schrödinger equation in its operator form. H acting on the wave function, given energy, time, constant energy as a constant value, times the same wave function. So, as I said, it's easy to remember if you, of course, understand that H is operator of the total energy, Hamiltonian operator of the total energy. And then for practical purpose, you really need to represent your operator of the potential, operator of the total energy as operator of kinetic energy, second derivative with respect to x times some constant, h squared over 2m. And yeah, operator of potential energy in general form, just some function which depends on the coordinate, right? What exactly is the function? You have to specify. You need really to know more about the system to figure out what would be this potential. Good. This is for one-dimensional case. What about three-dimensional case? For three-dimensional case, we will have x, y, and z coordinates. And then the Hamiltonian can be represented with this nabla operator. Again, nothing is really complicated. It's still the second derivative with respect to the coordinate x, but now we have also plus derivative with respect to the coordinate y, plus derivative with respect to the coordinate z. So what physicists do, instead of writing the three terms, because it's really annoying to write all of them, they just call this sum over second derivative with x, y, and z as nabla square operator. So just for shortness, for the simplicity of writing this equation. So if you see this nabla, it's nothing else, it's just taking second derivative with respect to each of the coordinates x, y, and z. So, and then the sum of each of these second derivatives with respect to x, y, and z. So then the Hamiltonian will have this form nabla, which means it's three-dimensional. You need to take derivative with respect to each coordinate. And now v also depends on x, y, and z. I put r. R is the distance. We know the distance should depend on all three coordinates, how we define it. So let's go quickly through some examples so you will feel more flexible when we talk about operators. As I already said, operator can be any mathematical action. It can be plus or multiplication or first derivative or second derivative, derivative with respect to one coordinate or with a second derivative, or like nabla operator. It means you take derivative, second derivative with respect to each of these coordinates. So any kind of mathematical action you can call as an operator. So what does it mean? So we have some operator A, any of this one, or maybe something else if you can think about any other, like integration, for example, also can be the operator. Or taking a power, second power, third power, also would be the operator. Any kind of operator, now this operator acts on a function, let's say f of x, and let's consider only a single one dimension, only one coordinate as a dependence. So some function f on x. After this operator acted on this function, we get a new function, g, which makes sense, yeah? You add number to some function, of course you change in this function. You multiply, you take a derivative, you integrate, whatever the action, you probably change this function. It's very natural to assume. So in general, when you act an operator on any function, you're getting some new function. However, it can be that you act the operator on a function and you're getting exactly the same function, just multiplied by some constant. If this is the case, so a is just a constant, after acting by operator on a function, you're getting a constant and the same function. The function is not changed. Let's say it was some polynomial having like x squared. After acting with some operator, you're still getting x squared times some constant, new constant. So if this happens, then what we say? We say that if operator doesn't change the function, then we say that this function is an eigenfunction of this operator, and this constant which you're getting in front of this function is an eigenvalue for this operator. So then if you think about our Schrödinger equation, h psi equals e psi. Psi and psi for the Schrödinger equation is exactly the same function, which means that you can say that Hamiltonian, which is acting on the wave function for this operator, since we get in the Schrödinger equation constant times the same wave function, it means that this wave function is an eigenfunction for Hamiltonian, and this constant A, the energy, is an eigenvalue of the Hamiltonian. So this is operator of the total energy acting on the wave function, and we get in the same wave function is not changed, times the constant, which means that this wave function is the eigenfunction of this operator, and this constant, the energy, is the eigenvalue of the Hamiltonian of this operator. In other words, Schrödinger equation is an eigenvalue eigenfunction equation for the energy. So you can formulate that your Schrödinger equation is an equation of motion of the wave for the standing wave, or you can also put it in a way that you just need to solve it for the eigenvalue eigenfunction problem for this operator. This formulation is used in the algebra. If you were taking mathematical course of algebra, where you talk about matrices, right, and kind of doing these operations with finding the eigenvalues, eigenfunction for matrices, it's pretty much the same as we're talking about finding this for the operator, finding eigenvalues, eigenfunction for the operator. So different ways how you can think about the Schrödinger equation. Because we do this, our main goal to be able to solve this equation, to code it and we solve it numerically with the computers. In a computer, as already said, this form is not very useful. You have to do it in a differential form through the derivative, second derivative for the kinetic energy, and then you need to know the function for the potential energy, then you can really solve it. Or you can put it in a form of matrices, like we do it in algebra, and then solve these eigenvalues, eigenfunction problems. So in the computers, in the codes which are used for the computers, it's actually doing through the matrices and doing this eigenvalue, eigenfunction problem as a standing approaches for solving this type of problems. And you will probably do this more with Dmitry during the class for the practice purpose to understand what does it mean that you can represent Hamiltonian as a matrix. And then find its eigenfunctions and eigenvalues. Okay, some examples. We still have a little bit, well, Dmitry said that we should be finished at 7. I don't know whether it's true or not. So that's why I'm saying that we still have 6 minutes before 7. So we have the function sine of x, right? This is our function. And let's say we have the operator very close to the kinetic energy operator, the second derivative with respect to the x. You need to show that sine x is an eigenfunction for this operator. Is it true? First of all, do you agree that sine is an eigenfunction of this operator? Yes?
I agree. I agree.
What about the other people? Do you agree or not? Is it eigenfunction? Yes or no? Or you don't know?
I'm not sure.
You're not sure. Okay, what did I say? If you take this operator and act on this function, and after you do this, you get in the same function, then it is the eigenfunction. Make sense? Then to answer this question, what you need to do? You really need to take the second derivative with respect to sine. Can you do it? What the answer would be? What would be the derivative from sine?
It would be cosine.
And what is the derivative from cosine?
It would be again sine.
Why?
Yeah. So if you take a second derivative from sine, you return back to sine, but I think you change in I think it's minus cosine, not
Minus, yeah, minus.
minus. But you take derivative from the cosine, first derivative from sine would be cosine.
Positive.
And then second derivative, then you take the derivative from cosine, you get in minus sine. The function is the same, right? The function is not changed after you're doing this operation. But what is changed? This constant.
Mhm.
Can you answer my second question? What is the eigenvalue?
-1.
Constant, which is in front after you're acting with your operator on the function, the constant what you have in front is the eigenvalue. In our case, it's -1, right? So yeah, because the function is not changed, sine is the eigenvalue of this operator, and the eigenfunction of this operator, and the eigenvalue is -1, because this is the constant in front of this the same function. Shows that the plane wave it's e to the power ikx, exponent of ikx, I is an imaginary I, k is a momentum, and x is a coordinate. And for our case, k just you can take as a constant because velocity would be the constant, momentum is a constant. So shows that this is the function. This is a function for the plane wave, and shows that this is an eigenfunction of the momentum operator.
Professor,
Yeah.
what is k and x?
X is a coordinate, and
Okay.
k is a constant which has a meaning of the momentum.
Okay.
So let's say momentum equals 5 per meter per second, meters per second, or whatever, 3 meters per second, 3 meters per second. Yeah. So operator for the momentum is first derivative times IH. I is imaginary I. Do you agree that this is eigenfunction?
Yes, for me, I agree.
Okay. What about I don't know your names and
Because, you know,
I need answers from other people.
Yes.
Why is it yes? Sarah, you said yes, right?
Yes.
Why you say yes?
I think by again imposing the operator here, it won't change
Yeah.
the function.
You take derivative with respect to x from exponent in a power ik. Ik is just constants, right? X. So you will get the same exponent. Exponent is not changing. The only thing which appears in front would be ik. So you will have the same function multiplied by ik. Ik is a constant. So when we take this derivative, we get in IH it just because we have it in a form for the operator, but this IH is multiplied by IK. Right? Because we take derivative from this power. IK is a constant. II gives you -1, right? According to the imaginary rules for imaginary numbers. So that's why minus times minus gives you plus. So I can rewrite it as HK. So overall, I'm getting my the eigenvalue for this operator actually would be HK. And since function is not changed, this plane wave is an eigenfunction for the momentum operator. HK would be the eigenfunction, eigenvalue for the for this operator, right? And its eigenfunction is the exponent in a power ikx. K is a constant which has a meaning of the momentum, the value for the momentum. Last minute, I know we go very quick, but I think you need, this is probably the most important slide because you will have now questions in your homework. And the homework is the last 2 slides in the lecture notes which Dmitry sent to you. This is a homework which you have to go through. So now we're ready to start writing the Hamiltonian for many electron atoms. What we have? We still have kinetic operator of the kinetic energy, which we know how to write through the derivative. And if it's 3-dimensional case, since we have x, y, z for the electrons being in an atom, this term we will write through the nabla. This is interaction. This is the term coming from the potential energy. This is an interaction between electron and nucleus, right? And since we have more than a single electron, there would be electron-electron interaction as well. So let's now try to make this kinetic energy operator and electron nucleus operator and the electron-electron interaction. For the kinetic energy, since we have 2 electrons, right, and I'm showing these 2 electrons interacting with this nucleus which has 2+ charge, 2+ due to the 2 protons in a helium atom. So each of these electrons can be characterized with their distance with respect to the nucleus, right? R1 for the electron number 1 and R2 for the electron number 2. So now our Hamiltonian for each of these electrons, which depends on their coordinates R1 and R2, can be represented as 2 terms in the kinetic energy. Kinetic energy for the electron 1, derivative, don't forget this nabla, derivative with respect to the R1. In other words, you can rewrite it as coordinate x for the electron 1, derivative, second derivative as a coordinate for the same electron with a coordinate y, and then derivative with respect to the coordinate z for the same electron. So this nabla operator is just second derivative for the coordinates of the electron 1 at distance r1, and this is the second derivative with respect to the coordinate r2 for the electron 2. 2 terms, right? Each of them multiplied by h squared over 2m. So this is for the kinetic energy. Now for the nuclear electron interaction, what we have? We have, again, this nuclei interact with this, and it's interact with this. But they have charges. So this is just Coulomb interaction between positively charged particle and the negatively charged particle, which we can write, if you remember how we did it in general physics. Z, the charge on the positive charge, Z value, 2 protons, right? 2+ for the nucleus. Then this is the charge on the electron, because there are 2 of them. It would be charge on the electron 1, charge on the electron 2. I put it e to the square, right? And divided for p epsilon naught. Epsilon naught is the dielectric constant of the medium, or of the vacuum in our case. So this is, and then the main part is 1 over distance between positive and negative charge of the particle 1 and positive and negative for the particle 2. 1 over R1 and 1 over R2. So this is, you again can call a constant, which depends on the charge of the nucleus and the charge of the electron. And this really depends again on the coordinate 1 over R1 plus 1 over R2. And finally, we get an electron-electron interaction. This is again Coulomb interaction between 2 negatively charges. They repulse, right? If plus and minus attract, negative will be repulsed, the same sign repulsing. It's a charge between 2 electrons, e squared over 4 pi epsilon naught, the same as we have here, right? And then it's 1 over, here we need to take the distance between these 2 ones, which is R1 minus R2. And that's why this is the most complicated term, because it really depends on the coordinates of R1 and R2 if this is changing, then this is changes, and they really depends now not just on the coordinate of the electron number 1 and the coordinate of the electron number 2. It simultaneously depends on the both coordinates. So that's why its term is having more variables rather than this or that or that or that. So this is our troublemaker. And pay attention, here's a positive sign. Yeah, so this is just, you can rewrite number operators through the derivative with x, y, and z, or you can represent it in a spherical coordinates, because we have a spherical symmetry. Electron is spinning around proton, kind of more like a sphere, right? So makes sense to go to the spherical coordinates, and I'm just showing you how you take this derivative with respect to the x, y, and z. If you put it in the spherical coordinates r, theta, and phi angles. So two terms, right? I mean, for each of them, we'll have this derivative with respect to the r, to the theta, and then to the phi. Or you can write it in x and y and z. And then you have to do the same for the second electron. Here we have negative sign because it's attraction. That's why energy going down, and you really have a negative term. This is positive term because it's repulsion. For repulsion, energy is increasing, and that's why it's a positive term. So this term has minus, like you can write it as two terms. This times 1 over R1 minus this constant 1 over R2, two terms here. And then you also have just one term, but with a positive charge, constant times 1 over R1 minus R2. If you have more than 2 electrons, if you go to lithium, I don't know, carbon, oxygen, then you can write this equation in the same way, thinking that now you have a sum over all electrons, how many electrons you have. For lithium, there will be 3 electrons. For oxygen, how many electrons? Oh my God, I guess it's 8 electrons in oxygen, and so on. So this sum goes over number of electrons you have in an atom, right? And then for each of them, you have to take a second derivative with respect to the coordinates, either in a spherical, or you can put it in x, y, z. Then you have a sum for the interaction between nuclear and electron, 1 over R1, 1 over R2, 1 over R3, and so on, right? This will be each term, this R will be different for each different electron. And you have a sum, all of these guys. And here we have also a sum over the, because we have R1 minus R2, so we have a sum between difference in, when you fix in one electron, and then find the distance with electron number 2, electron number 3, electron number 4, 5, and so on, right? So I'm putting two sums. You kind of say this sum, you fix electron 1, and then see how this electron 1, let's say you fix this one, and then find distance to this electron, let's say distance to that electron, that electron, that electron, that electron, and so on. Done. This would be going through one sum, this fixed I equals 1. Then you go I equals 2, means you go to this electron, and now again finding the distance between this and then another one, and another one, run over this one, and so on. That's why you need two sums. You fix one electron in one sum, right? And then look all over other electrons to subtract in this term. This is I. Oh, this should be J, by the way. It's an error in my slide. It should be J going through the second term. And of course, we're not taking the distance of the same number electron, but it's 1 and 1, right? That's why we say J never equals to the same index as you have in this sum. If you have now more than a single atom, if you go to the molecules, then you have the same kinetic energy, right? For each of the electrons you write, then you have again interaction between nuclear and electron for each of the atom. Then you have the electron-electron interaction inside each atom. And then you will have the nuclear-nuclear interaction, since you have now more than one nuclear in a molecule, since you have many atoms now. If you open each of this term, okay, just to finalize, this would be the way how you represent this kinetic term, sum over each of the electron, how many electrons you have in each atom. Then you have another term for the nuclear electron interaction, and I just have this constant being kind of taken out because this constant will be the same for each of these terms. Here now, two sums, because you find the distance big R, this is nucleus, let's say nucleus from atom number 1, and then you check in each electron for this atom at this distance, right? Then you move into the nucleus number 2, and again, changing the index for each electron from this nucleus, and so on. That's why, again, same idea, you're having two sums, but this now going over position of the nucleus and difference between position of this nucleus minus position of this electron. Electron number 1, number 2, number 3, number 4, with respect to nucleus number 1. Then you change in this nucleus to the nucleus number 2, right? And go again through the electron number 1, 2, 3, 4, and so on. Finally, we get in this term for the electron-electron interaction. Again, two sums in the same way. You fix in one electron and then check in the distance with respect to the electron 2, 3, 4, and so on. And then here is the interaction between nucleus, which again, just the difference between nuclear position. Two sums, you fix in nucleus 1 and check in what would be the distance between nucleus number 2, nucleus number 3, nucleus number 4. So big R and big indexes I and J goes for indexes 1, 2, 3 for nucleus, right? And small r and indexes I and J, which are small, go through the indexes with respect to the electrons. So, yeah, pretty much the same idea. Just showing that, yeah, don't forget about these constants. We have 1/2 to avoid the repeating summation for the same I and J, I and J, I and I, big I and small I for these terms, requiring this 1/2. In this case, it's 1/2. Here, they always will be different since we fix I for electrons and I for nucleus. That's why one for this R and one for this R are different. That's why you don't need to take 1/2 here, since you never have the same term. Here you might have the same electron if you're not changing, if you take the same J and I, right? So that's why we need this 1/2. Okay, so I'm done. In your homework, you have to apply these expressions, but really writing each of these terms, depending on how many electrons, how many nucleus, how many this or this term you have for each of the case. You will be given the molecule, H2, hydrogen molecule, right? Or HO or something like this. And you need to write each of these terms as a sum over this guy, over that guy, over that guy, over that guy. So hopefully you will be able to do it by yourself. If not, you can, I'm pretty sure Dmitry will probably go through some examples in his next lecture, I think probably Wednesday, and you will have some more training for applying this idea to the actual molecules. I overuse the time completely, more than 10 minutes. I'm sorry for this. I will send these slides to Dmitry, and then he will send it to you sometime today. Probably by tomorrow you will get the slides. But the same information, you can find pretty much the same information, just in a different representation, different way of presenting it from Dmitry's slides. Are we good?
Okay. Yes, thank you.
Okay.
Yeah, thank you.
Yeah, thank you for listening and taking more time than it is expected.
Thanks, Doctor.
Yeah. So then, have a nice evening, and I guess Dmitry will see you on Wednesday for his lab, for his practice part of this course.
Okay, thank you.
Are you good?
Bye.
No questions? Probably a little bit overwhelming, but if you really think about all these things, maybe it will be not so complicated. It's complicated, but not so much as it is since now.
Mm-hmm.
I guess we're done.
Bye.
Bye-bye.
Goodbye.
Okay, bye.
Professor, can I ask question?
Yeah, just disconnecting.
Okay. Before disconnecting,